I will be running the different variants of um, algorithms in calculating the approximate value of pi. So we are given three variants. The first variant will just given the input R, you will be generating pair of x and y axis and determine whether the generated pair of x and y axis is inside the circle. This condition and increment the count. Else, increment the count outside in order to calculate later on the value of pi. Um, we are asked to test this specific variant in the given value of r for 10, 100, 1000, and 1000, and see how it is computing for the value of pi or approximating the value of pi, and compare the generated value on the actual true value of pi. Now, we will be running the first variant, and let's see how it's gonna output. Here, I'm just doing a counter in each value of x until it reaches the given value r, and I just want to output every 200 the current value of pi so I can see the progress in the console, and then after the full iteration, I will just output the final value of pi with this label final. So since our first input of R is small, starting 10, I won't be seeing this since it doesn't reach 200 yet. So we will see this output on the later on bigger values. So let's run the first variant using R equal to 10. Okay. Here, you'll notice that given the R is 10, it will generate R squared number of dots inside and outside the circle. So this is the actual generated value of the pi given R10. So I will be recording all these results in a separate spreadsheet and then show it once I've done running all the test inputs. I'll be plotting them in a spreadsheet and to see the difference, or how the input affects the precision of calculating the value of pi based on the input. So this is the record. Then this is the first calculated pi value given the R10. So you'll see here that it's still far from the known value of pi, which is around 314,1592. So 314,1592 is far from 2759. So let's move on to the next input, which is 100. So I'll be changing the value of r here in one, which is 100, the next input, and then run it. So here we're still not gonna see the previous value calculated in every 200 interval. So we'll just see the final output given that the r value is just 100. So here you'll see that relatively it's closer based on 10. So it produces a more precise value of pi, 3.10, compared to 3.1415 value of pi, compared to the previous round, which is 10. So I'll be recording this generated value as well for the R100. Now moving on to the next input, which is 1000. I'm running the variant one again with our value 1000. So here you'll be seeing now the progression every 200 interval of value of x. So as you can see, as the value of x grows, the more it generates a precise value of the pi. So here the first 200, second 200, etc. And then the final calculated value of pi, 313,754. the rest. So you'll see here that given that the R 1000, it produces a more precise value of pi with the variant 1, wherein we define the value of R. So the last output or test we will be doing is at 10,000. So this is the part where we start to see the the algorithm breaking and producing a very far value from the pi for some reason. So given the R 10,000, I'm running now the program for the variant 1. And you see here the progression of the generated value pi. So you'll see slowly it's trying to reach the going near the known value of pi until it reaches the final one. But yeah, it seems to be at this rate, given R 10,000, the algorithm started to break and run a little bit slow. Now let's just wait for this to output the final value, and then we'll be recording. So you'll see here the final output is it's really far from the the known value of pi for some reason, given the large input value of R 10,000. So just for the fun of it, I was playing around with variant 1, and I was trying to find the sweet spot where it's trying well where it's going to generate the most accurate value of pi. So I've run it in 4,000. So run it. So you'll still see here that it's still accurate. It's actually pretty accurate at R 4,000. And then so yeah, I'll be recording this value as well given the R 4,000. And then let's use a little bit higher number and increment the R by 500. Okay, now you'll see here that every interval of 200, it's still going near the real value of 5. For this output, it's 3.60914069080. So it's at 4,500, it's still stable and producing a precise value of pi. Now, if we reach the 5,000, this is actually the breaking point. So 5,000 is half of the last test value given test value 10,000. And based on my observation, starting to break at that point at 5,000. So you'll see here. Here. So it's still better compared to 10,000, but at 5,000, it's already far from the actual value of pi. So all the I plotted the output for 10, 100, 1,000, 10,000, and my additional test data for 1,000 and 4,500 in an Excel sheet. And this is the actual generated values. So this is the value of R test data, and this is the known value of pi, and these are the output. So you'll see here that at 10,000, it's already far. So the variant 1 is breaking already with higher input of value. It's really far from the actual value of pi. Now this is the additional test data where I was trying to find the sweet spot at 4,000 and 4,500. It's really generating a precise value of pi, and at 4,500, this seems to be the sweetest spot for the test data I used. At 5,000, this is the point where I think it's starting to break, and it's no longer in a uptrend graph in generating the value of pi. Now for the frequency count, as the frequency count chart and against the size input for variant 1, this is the actual output. This is the actual graph generated here. So so the value of R, I've included the additional for 4000 and 4500. And this is the frequency count wherein it's r squared of r, which is used as the y-axis, and the x-axis being the value of r. So you'll see here the points that it's in this form. So technically the I think it's an O of n, wherein as the input increases, the frequency count increases as well. But the output, it's not it's it's not precise as the value of r as the value of r increases. So that's variant 1. We were instructed not to no longer discuss variant 3, since variant 3 is actually just a small variation of variant 1, wherein you are just simply converting the integer x and y pairs into a real number based on the given value of r. While for the variant 2, we introduce the randomness in generating the dots, whether it's going to be inside and outside the circle. So in variant 2, let's play this one. In variant 2, what it does is, unlike variant 1 where you provide the value of r and then produce the number of dots r squared, in variant 2, you will be giving n, which represents the number of times that you will be generating the dots. So we were asked to test this algorithm in this input 10, 100, 1000, 10,000, 100,000, 1 million, and 10 million, and see on how it behaves, on how it produces the value of pi as the value of n given. So value of n represents how many times we're gonna randomize producing x and y pair, and determine whether it's gonna be inside and outside the circle with this condition. Similarly, in variant 1, every interval of 200, I'll be doing the output of the computed pi, and at the end, I'll be displaying the final output here. So let's first run it at 10, the variant 2. Again, I won't be running the variant 3 anymore. It is assumed that it's just gonna have the same output as variant 1. So let's run now variant 2 at n equal to 10. Okay, so here you see that it will, at given value of n equal 10, it already produces a little precise value of pi. It's at 3.2 at the n having a value of only 10. So let's see on how it behaves if we increase the value of n to 100. So it's getting closer. So we'll see the trend that as the input as the size of n increases, it gets closer to a more precise value of pi. So this at 100. So similarly in variant 1, I will be recording the generated values here in a similar spreadsheet. So we'll see it better later. So we are already at n100, and you'll see that it has a better precision in calculating calculating the value of pi. So let's move on to the next test case for 1000. Run the program. So you'll see here now the progression of every 200 interval. So at 1000, you'll see here the first 200, second 200. So it's getting closer and more accurate as the size of n increases, and the final output for the 1000 is this one. So since there's a factor of randomness here, it's not gonna be consistent on the final output. So you'll see here at 1000 it generated this, but if I run this again without changing the value of n, we are not expecting to see these numbers again. So let's see, it's 30920. If we run it again with the same value of n, given the the randomness, you'll see here that it's running, it produces a different and actually more accurate value of pi without changing the input or the size of n. That's because of the factor of randomness. So yeah, that's how it's gonna be. But you'll see that still the trend here is that as the value of n increases, the more precise it produces the value of pi. So that's at 1000. Now let's move on to the next input, 10,000. Run it. So here you have a very good number of pi here at 10,000. It's 1431, and yeah, similar trend here at 10,000. You'll see that every 200 interval it gets better and better in trying to calculate the value of pi, and it's getting closer to the actual value of pi. So that's 10,000. Let's move on to 100,000. Okay, same trend here. It's at the latter part or the last 200s. It's getting better. It's getting better of going to the actual known value of pi here at 100,000. So let's try 1 million. Okay, so it's gonna be producing a lot of 200 interval values, but it's still the same trend that as the size of n increases, the value of the generated value or the calculated value of pi, it's going nearer and nearer the actual known value here. So the final output of pi for input 1 million is at 3.13929. So again, I've recorded I will be recording these values and put it in a spreadsheet, and then so we can do a final analysis later on. So let's go on to the last test input for variant 2 with randomness, which is 10 million. 3, 1, 2, 3, that's 10 million. Then let's run the program again and compare it to the other output. So you'll be seeing here a lot of 200 intervals output, and you'll see at the very end it produces a very good value of pi at 10 million as value of n. So still the same. The statement still true that as the size of n increases, the more precise value pi is being generated in variant 2. So now let's look at the actual generated test data for variant 2 here. So we use these are the used value of n. These are the generated or the calculated value pi, and compare it to the actual value of known value of pi. So you'll see here at the last test we did at 10 million, you'll see here that it is the closest actually. This is a bit over, so again there's a factor of randomness, so it's not that consistent. But here at 10 million, it's actually based on that run, it's the nearest in the actual value of pi, so better approximation. Now for the frequency count against the value of n or the size for variant 2. So we know that the value of n actually represents on how many times it's going to iterate and produce the dots inside or outside the circle. Hence, it will just be a straight graph. So it's still an O of n. So the frequency count still based on the the given value of n.